Okay, welcome back. Enough background. Let's actually get into the heart of the matter here. So you remember we were back in the 1880s, and we were talking a little bit about atomic spectra, and we said that certain elements give off certain colors when you burn them, which is pretty and great if you're making fireworks. But what does that really have to do with chemistry, and what does that have to do with the electronic structure, which is what we're talking about? Well, it turns out it has a lot to do with electronic structure because atomic spectra are produced when an electron moves from a higher to a lower energy level, giving off light in the process. So if I know something about the light that's given off and the color, which of course corresponds to a certain wavelength, as we talked about in the electromagnetic spectrum, what that does is that gives me insight to how the electrons are arranged around an atom. And that's really, as a chemist, what I'm interested in. Because if I know that, now I can correlate that back to how it will react, which is ultimately really what I'm interested in. So that's what spectroscopy really is. We study the light given off, whether it be visible or infrared or ultraviolet or whatever, in certain processes. And then from that, we correlate that back to how the electrons are arranged around an atom. Make sense? So, for example, here's kind of a picture of what's going on here in an atom. So I have, turns out there are only certain discrete amounts of energy that an electron can have around the nucleus. So it's kind of like stair steps. You can be on the first step, you can be on the second step, you can be on the third step, but you can't be on the 2.5 step. If you try, you're going to fall down. The lowest energy that an electron can have in an atom is E1 here, and that's called the ground state. So when you hear the term ground state, that's the same as E1. So an electron in an atom can either have this much energy, this much energy, this much energy, so on and so on and so forth. So let's say, for example, I took a piece of copper wire and I put it in a Bunsen burner flame. Well, I'm going to give those electrons energy, okay, and we're going to do what we call excite the electrons, all right? And so what they're going to do is they're going to hop up from a lower energy state to a higher one. So let's say, for example, I had an electron sitting here in a copper atom, just minding its own business, sitting down there in the ground state, and all of a sudden I stick it in a flame. Well, what it's going to do, it's going to absorb energy, and that's going to kick it to a higher energy state. Now, that electron could either absorb enough energy to go here, or here, or here, or here, and there's actually an infinite number of these. I just got tired of drawing at 5. They don't stop at 5. And it will absorb that much energy to hop up to here, 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 but never in between. All right. So let's say, for example, that electron absorbed enough energy to hop up to E3 here. All right. Well, does it really want to be up there? Well, no, because remember, all things being equal, atoms and electrons and students prefer to be in the lowest energy state possible. So it doesn't want to be up here. So what it's going to do is it's either going to drop down to here, or it could drop down to here, but never in between. So let's say, for example, it goes from E3 down to E2. All right. When that electron hops down from E3 down to E2, now it has less energy. I can't create energy. I can't destroy energy. So that energy's got to go somewhere. So where does that excess energy go? Well, what's done is it's thrown off in the form of a photon. In other words, a little tiny packet of light. And that's the light that you see. All right? Now, if I know the wavelength of the light thrown off here, I know the energy of that light. If I know the energy of that light, well, now I know the energy difference between these two energy levels. See? So delta E here between my two energy levels is equal to E high minus E low. In other words, where I was up here at the beginning, down to where I was at the end. That's equal to the energy of the photon that's thrown off. Well, how do I figure out the energy of the photon thrown off? Well, I have a couple equations for that, which we talked about in the last video. I know that E for a photon is equal to h times nu, where nu is the frequency of the photon, h is that Planck's constant. And what's nu? C over lambda. So therefore, it's also equal to h times c over lambda. All right? So basically what I can do is I can measure the wavelength of the photon thrown off. That's going to tell me the energy difference between my two energy levels. I'm correlating something I can see to something that I can't see. Make sense? Okay, well, let's take a look at sodium, for example. Sodium's a nice simple spectrum here. Here is a yellow line somewhere around 589. That's this little guy right here, probably. Okay. For that yellow line in that sodium spectrum, calculate the energy difference between the two energy levels involved in joules. And just for fun, let's go ahead and calculate it in joules per mole of electrons as well. All right, so how am I going to do that? Well, I know that delta E is equal to the energy of the photon, which is equal to hc over lambda. All right, so I know that h is 6.626 times 10 to the minus 34 joules seconds. That's a constant that would be given to you on a test. I give you constants. That's Planck's constant. I know that c is 2.998 times 10 to the 8th meters per second. That's a constant. Of course, I would give you that on a test as well. And so what's my wavelength? Well, it's 589.0 nanometers. All right, well, notice this is in meters per second. If this is in meters per second, my wavelength has to be in what? What's got to be in meters for these to be able to cancel. All right, so I need to convert this to meters. So you could sit there and you could do 1 nanometer is 1 times 10 to the negative 9th of a meter and do it factor label and figure it out that way. Or here's just a really simple way to do it. You know, 1 nanometer is what? 1 times 10 to the negative 9th of a meter. So 589 nanometers would be what? Well, 589 times 10 to the negative 9th of a meter. See? And just plug it in that way. Now, is this strictly in scientific notation? No, it's not in scientific notation because this number has to be between 1 and 10. But here's the really good thing. It doesn't matter. If you punch it in as 589, hit your EE key, and then put the minus 9 in there, your calculator will actually move the decimal for you. And it will actually move that to 5.89 times 10 to the minus 7 meters. All right. So yeah, just punch it in as 589 times 10 to the negative 9th, and the calculator will do it. So you got this times this divided by that. Notice that my seconds, inverse seconds here, seconds on the bottom, seconds here cancel. I've got meters here, I got meters there. What's the only unit I have left? Joules, which is what I'm looking for. And so I run that through the calculator. You can do that if you want to. You should get something similar to 3.37 times 10 to the negative 19 joules. Okay, and that's for that one electron making that transition. All right. Is that a very large value? No, it's not a very large value. Is that something you could probably see? Probably not. Well, what if that's not the only electron making that transition? What if I had 6.022 times 10 to the 23rd little electrons hopping from that high energy level down to that low energy level in sodium metal when it's burning? That's a lot of electrons making that transition, each of them throwing off their little photon with a wavelength of 589 nanometers. Do you think it might add up to something you could see? Well, let's check. Okay, so I know that I've got 3.37 times 10 to the negative 19 joules per electron making the transition. What I want to do is I want to get that into kilojoules per mole, or at least joules per mole of electrons making the transition. Well, I know that there are, in 1 mole of electrons, there are 6.022 times 10 to the 23rd electrons. That's what a mole means. Okay. Notice I put the electrons up here to cancel these electrons here. So what am I left with? Well, I'm left with joules per mole of electrons making the transition. Let's go ahead and convert that to kilojoules. That's going to be a pretty big number. So how do I get from joules to kilojoules? Well, I know that 1 kilojoule is equal to 1,000 joules. What goes on top, what goes on bottom? joules on the bottom. That way we get kilojoules left up here. So my joules cancel. So I'm left with kilojoules up here on the top. I'm left with moles of electrons down here on the bottom. So you end up with kilojoules per mole. So you got to be able to that stoichiometry or just dead in the water here. All right. So now we do the math. 3.37 times 10 to the minus 19 times 6.022 times 10 to the 23rd. Divide that by 1,000. And you come up with a number like 203.1 kilojoules per mole. All right. Now, is that an appreciable amount of energy? Yeah, that's an appreciable amount of energy. Is that something that you probably could see with the naked eye? Yeah, that's probably something you could see with the naked eye. So what that tells us is this. There's two energy levels in a sodium atom, and they differ by 203.1 kilojoules per mole. And when you look at the spectrum of sodium, that's what's causing this line right here at approximately 589 nanometers. Electrons transitioning between those two energy levels. All right. Now you'll remember we talked about how an electron can either be here, 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 or here, but never in between. Well, that doesn't make sense to you and me. You know, we look at a particle and we think, well, it can have any energy it wants in between. But in reality, it can only have certain discrete amounts of energy. Energy is what we call quantized. All right, it's like stair steps. So why don't we see that? Well, look at the energy difference between those two energy levels. Teeny, teeny, tiny. All right, and in fact, so small that up here in our world, we don't see that. So it looks like a ramp instead of a staircase. But if you were able to get close enough to the ramp, you would see little tiny teeth. You'd see little tiny steps there. And so when you get down to the world of the very, very small things that are moving very, very fast, these quantum effects do show up, even though you can't see them up here. Because the staircase is so tiny, it just looks like a ramp to you and me. But yeah, when you get down to the world of electrons here, you've got to take those things into account. All right? And so what I can do now is I can go back to these spectra here, and I can actually look at these lines here. I can calculate the wavelength, and I can actually calculate the energy difference between the two energy levels involved in the transition. So now what I'm doing is I'm actually getting some sort of information from the spectra which correlates back to electronic structure. So we're making progress here. Oh, and by the way, the reason we know that the energy is quantized is because if it wasn't, if every electron could have any energy it wanted to, what would you see here? Well, you'd see this. You'd just see a continuous spectrum, see? Wavelengths of light being given off everything. The fact that I only see certain wavelengths of light given off and nothing in between here ever, that's what leads me to believe that my energy levels can only be certain values. So we're making progress here. We've correlated this with the energy levels in a particular atom, in this case sodium we were talking about. But we still have a bit of an issue here. Which two energy levels are differ by 203.1? Is it 1 and 2? Is it 2 and 3? Is it 1 and 4? Is it 10 and 17? Is it 5,260 and 6? Don't know. See, at this point, I know there are two energy levels in the sodium atom that differ by 203.1 kilojoules per mole, but I can't tell you the top one. I can't tell you the bottom one. And I don't even know which two they are. So there's still quite a few questions to be answered here. We've also got another problem here. Here are the spectra for sodium. Here's hydrogen, here's calcium, and this is mercury right here. Do you think the energy levels and their spacings are exactly the same in all four of those atoms? Yes or no? Why or why not? Well, if the energy level spacings were exactly the same in every single atom, what would you see here? well, you would see lines in exactly the same space. See? So all the spectra would look exactly the same. Do they all look the same? No, they don't look the same. None of them look the same. They're like fingerprints. All right. So what does that lead me to believe theoretically? Well, that leads me to believe that the energy spacings in each of these atoms is different, because otherwise the spectra would all look the same. So I know there's two energy levels in a sodium atom that differ by 203.1 kilojoules per mole. I don't know the top one, I don't know the bottom one, and even if I did, that wouldn't work for hydrogen, calcium, or mercury. So we've got a ways to go here. But we're starting to make progress, I guess. Okay? All right, well, if you were going to do this, if you were going to study electronic structure and spectra, would you start with sodium? What would you start with? Well, I'd probably start with hydrogen. Why would I start with hydrogen? Well, the neat thing about hydrogen is there's only one electron. See, in a sodium atom, I have, 11 electrons? So I don't know the top level, I don't know the bottom level, but I don't even know which electron's making the transition. Is it 1? Is it 2? Is it 11? Don't know. So when you come across a complicated problem, you always want to start with the simplest case first. Solve that and then try to work your way up. You don't start with the hardest homework problem first, right? So hydrogen would be a good place to start, because at least you know there's only one electron making the transition. So that simplifies things quite a bit. And if you thought that would be a really good idea, but unfortunately you're about 150, 200 years too late, because a fellow by the name of Niels Bohr came along in the 1880s, and that's exactly what he decided to do. He decided to study hydrogen and figure out something about electronic structure from that. And so Niels Bohr came up with a model of the hydrogen atom. This is the Bohr model. And it looks a little something like this. Bohr postulated that an electron moves about the nucleus in a circular orbit of fixed radius. By absorbing energy, it moves to a higher orbit of larger energy. Energy is given off as the electron returns. All right, so let me draw you a picture of what Bohr thought an atom looked like. So this is a hydrogen atom. I've got my little proton sitting here in the middle. And then I've got this little electron whirling around here around the outside in a circular orbit. You ever seen anything look like that before? Yeah, you probably have. That's your standard kind of planetary model of an atom, the ones they drew for you back in 6th grade. So yeah, this is nothing new to you. It was new to people in 1880, though. In 1880, the standard model of an atom was probably J.J. Thomson's plum pudding model. And basically what he said is you have this big, giant, huge, gelatinous blob of negative charge. Okay, and within that gelatinous blob of negative charge, you have localized regions of positive charge. So they were kind of like the plums in a plum pudding. That's why they call it the plum pudding model. And that's what people thought atoms looked like back then. Bohr was one of the first people to actually take that electron outside the nucleus. So it was actually a fairly revolutionary idea for the time. It just doesn't seem like it to you and me because we're kind of used to that. All right. So how does all this stuff work? Well, here's what Bohr said. He said, okay, I've got this electron that's got a certain amount of energy whirling around the nucleus here. When that electron absorbs energy, what that does is that kicks it up to a higher orbit. The further you are away from the nucleus, the more energy that electron has. It doesn't want to be in that higher orbit, so what it's going to do is it's going to return to a lower orbit, and when it does, it throws off that photon, and that's the light that you actually see. All right? But Bohr went even further than that. Turns out that Bohr can tell you the energy of every single energy level in a hydrogen atom. Every single one of them. Okay, and he came up with this nifty little equation, which, by the way, your book actually has a different equation. It's the same thing. I just do this slightly different so you can see how things work here. So if you want to use that equation in the book, that's fine. You want to use this one right here, then it works as well. but it looks a little something like this. This is Rydberg's constant here, by the way. Might give that to you. We'll see what we can do. E sub n, in other words, the energy of any energy level on a hydrogen atom is equal to negative 2.18 times 10 to the negative 18 joules over n squared, where n is 1, 2, 3, 4, so on and so on and so on and so forth. All right? E1, basically you plug in a 1 right here, and that tells the energy in the first energy level, or what we call the ground state. Okay, E2, if you plug in a 2 here and then use this equation, that tells the energy in the second energy level. E3 and E4 and so on and so on and so forth. Okay, so let's see if it works, because, you know, theories are only good if they're actually experimentally provable. Calculate the wavelength of a photon thrown off when an electron moves from n equals 3 down to n equals 2 in a hydrogen atom. What is the energy in the third energy level of a hydrogen atom? Well, we simply take our little equation right here, and we're going to plug in a 3. Okay, so negative 2.18 times 10 to the negative 18, it's an 8 there, divided by 3 squared, of course that's 9, and you get negative 2.42 times 10 to the negative 19. Okay, now, don't get too freaked out about the negative sign here. You know, it's negative energy. How can you have negative energy? Well, it's a sign convention thing. All right. In physics, anytime you have a bound system, say for example the Earth revolving around the sun, the total energy of that is negative. If I gave the Earth just enough energy to escape Earth's gravitational pull, the sun's gravitational pull, the total energy of the system is now 0. If I gave the Earth more energy than it needed to escape the sun's gravitational pull, the total energy of the system is positive. All the negative means here is this is still a bound system. In other words, the electron is still whirling around the proton. Okay, so that's all that means. You know, if I gave that electron just enough energy to escape that proton, this would be 0, which actually corresponds to E infinity. Which, by the way, actually you can calculate the ionization energy of a hydrogen atom that way, because that's kind of what you're doing. You're theoretically taking that electron and you're moving it an infinite distance away from the proton. But yeah, that's how you calculate the ionization energy there. All right, so that's what the negative means. Don't get too freaked out about it. It's a sign convention thing. All right, what about E2? How do I calculate that? Well, I just simply take this equation. I plug in a 2 down here. So negative 2.18 times 10 to the minus 18 divided by 4. And I get negative 5.45 times 10 to the minus 19 joules. Okay? Which one of these is higher in energy? Well, E3 is higher in energy. But 5 is greater than 2, right? Well, what's negative? Negative 2 is greater than negative 5. Because you're closer to 0. So, yes, this is a larger number because it's negative, not absolute value wise, but larger number. So yes, E3 has more energy than E2, even though the number is that negative there. Okay, so how do I figure out the energy difference between the two? Well, I just subtract. So I'm going to take E3, my high one, I'm going to subtract off E2. So I got negative 2.42 times 10 to the minus 19 minus a negative, be careful with the signs here, minus a negative 5.45 times 10 to the minus 19. When you subtract off a negative, that's the same thing as what? Adding the positive. So you're going to add 5.45 times 10 to the minus 19, and you'll get 3.03 times 10 to the negative 19 joules. Positive difference, which makes sense because you're taking a big number, subtracting off a little number. All right, and that's the energy difference between the third energy level and the second energy level in a hydrogen atom. All right, so how am I going to figure out the wavelength of the photon thrown off? Well, I know that delta E here is equal to the energy of the photon, and I know that that's equal to hc over lambda, which is the wavelength here of your photon. Well, I could take that and I could just solve this for lambda. See, I could multiply both sides by lambda and then divide by delta E and just rearrange that, and I get this little equation right here, and now I just plug the numbers in. So I've got 6.626 times 10 to the minus 34 joule seconds times 2.998 times 10 to the 8th, should be meters per second, ran out of paper, divided by 3.03 times 10 to the minus 19 joules. Joules cancel. This is meters per second. Your seconds cancel. And so really the only you have left here is meters. Okay, and my wavelength ends up being, when you run it through the calculator, 6.56 times 10 to the negative 7 meters. Okay, but we like to express wavelengths of light in what? Nanometers? So how would I get that to nanometers? Well, I know that 1 nanometer is 1 times 10 to the minus 9th of a meter. So 1 nanometer on top, 1 nanometer on top, 1 times 10 to the minus 9th meters on bottom. So those cancel, or just multiply by 1 times 10 to the 9, either way. 656 nanometers. Well, again, theories are only good if, number one, they make predictions. If you have a theory and it doesn't make any predictions, it's a useless theory. You know, it's like having a socket wrench that doesn't fit anything. You might as well just throw it away because it's just kind of hanging around. So theories have to be experimentally verifiable, have to make predictions, and those predictions have to come true. If I have a theory that predicts the sky is purple, it's a bad theory, because the sky is not purple. The sky is blue, right? Okay? So here's what Bohr is saying. He's saying, okay, when an electron hops from E3 down to E2 in a hydrogen atom, I ought to see a photon being thrown off, and that photon ought to have a wavelength of 656 nanometers. So how are we going to check that? Well, let's go to the spectrum. So here we go. This is the spectrum of hydrogen over here. And we go over to, look at there, right there. Little orange line sitting in the hydrogen spectrum, right? Wonder where that is. Well, that's exactly at 656 nanometers. Right there where Bohr predicted. Pretty cool, huh? Not only can Bohr tell you that this is going to be here, he can tell you this line ought to be here. He can tell you, he can actually predict what the spectrum for hydrogen actually looks like. Okay, and he can tell you which energy level the electron is coming from and which level the electron is going to. So that's considerably better than where we were 20 minutes ago, right? Interesting. This is the first line in something called the Bohr series. And what the Bohr series has in common is they're all visible. You can see them. Okay, and that's what those lines are in that hydrogen spectrum. They're in the visible range. Okay. The other thing that the Bohr series lines have in common is they're all transitions down to n equals 2. All right. So for example, from 3 down to 2, that's the one we looked at. There's another one from 4 down to 2, 5 down to 2. 6, 7, 8, 9, 10. Goes down to n equals 2. It's a Bohr series line that's visible. All right. So how did Bohr come up with all this? Well, he kind of reverse engineered it. He actually looked at the lines in the spectrum, and he kind of came up with an equation that kind of fit what he saw. So that's not really cheating. You could call it cheating if you're a theoretical chemist, but you know, sometimes we use experimental data too. So yeah, it worked. Okay? And it worked really, really well. Now there's another series of lines called the Lyman series. By the way, you know how I remember this? I always think that's the Paschen series, and the other one is the Lyman. So what I do is I just think of it the way it is, and I just switch it around. That's the only way I can remember it. Sometimes when you're not that bright, you just have to have tricks. So this is the Lyman series that goes down to the ground state. Okay, down to n equals 1. These have more energy. See, there's a larger energy difference than my Bohr series here. So would you expect that wavelength to be shorter or longer than visible light? Well, it's going to be shorter. Larger energy, shorter wavelength, higher frequency, right? These happen to be all found in the ultraviolet spectrum. Okay. Can Bohr see into the ultraviolet spectrum in 1880? No, he can't. Can he predict where the lines ought to be? Yes, he can. We can see into the ultraviolet spectrum here in 2021. Are those lines there? Exactly where they're supposed to be. There's another series of lines that goes down to n equals 3. This is called the Paschen series. Smaller energy differences, so therefore you would expect longer wavelengths, lower energy, and these are actually found in the IR spectrum. Okay? Can Bohr see into the IR spectrum in 1880? Can he predict where the lines ought to be? He can. Are they there? Yeah, they're right there. So Bohr has a theory that not only works for what he can see, but it also works for what he can't see. But we can see it now, and yeah, it works great. Works great for all three. So that's pretty good. That's a lot. That's a good work there. By the way, do you see how these lines are not equally spaced? Okay, that is a consequence of this n squared in the denominator here. So the way I drew it for you earlier, where they were all equally spaced, is not actually accurate. Now we have to refine our theory a little. It actually looks more like this. The lines get closer and closer together as you go. All right? Okay, well, that's great. Well, what are you going to do now? You still got half a career. You got time on your hands. Where are you going next? Well, how about helium? Why helium? Well, I only got 2 electrons in helium, so that's the next simplest case, right? So maybe that's where I go. Well, that's exactly what Bohr did. So Bohr tried to use the same equation here on helium. Did it work? Well, no, because the spectrum for helium is different than the spectrum for hydrogen. Well, maybe I just changed the constant up here. Maybe that works. Does that work? No, doesn't work. Well, maybe I come up with another equation. Does that work? No. In fact, nothing else works. Bohr has got hydrogen completely whipped out, but he can't find an equation that works for helium, or lithium, or beryllium, or boron, or carbon, or any other element in the periodic table. So it's a theory that only works for one atom. If you happen to be studying hydrogen, it's a great theory. But if you happen to be studying anything else other than hydrogen, not a great theory. Doesn't work at all. So what's going on here? Why doesn't it work? Well, there's a couple of reasons why. One reason why is because when you get to helium and higher, you run into something called in physics a many-body problem. A many-body problem is a problem where you have three or more interacting bodies with each other. In physics, if n is equal to two bodies, we can solve those completely. If you have like the Earth and the Moon, you can look at the gravitational pull of the Earth on the Moon on the Earth. You can look at the orbit and this and that, and you can predict exactly where the Moon is going to be 10,000 years from now, or where it was 5,000 years in the past if things are still moving the same way they were. No outside forces there. No problem. We can do that. When you have three interacting bodies with each other, you can't solve that completely unless you constrict the motion of them somehow. All the motion has to lie in a plane, or the mass of one body is much, much, much greater than the mass of the other two. We can't do that. So if you had the sun and the Earth and the Moon, and you wanted to solve that completely without approximations, can't do that. We still can't do that. We can't solve any problems besides greater than n equals 2. All right, it's called a many-body problem. If you can figure out how to do that, that is probably going to be the greatest scientific discovery of the 21st century, because it just has so many different applications. So work on that this weekend and see what you can come up with. But people have been trying. All right. Well, if you think about it, helium is a many-body problem, because what you've got is you've got a nucleus in there which has 2 protons and 2 neutrons, but you can assume it's one big particle of a charge of +2. That's okay. But then you've got 2 electrons whirling around. Okay. And the proton and each electron are interacting, but the 2 electrons themselves are also repelling each other. So you've got 3 bodies interacting with each other, and we can't solve that. There are approximations we can make to where we can get an answer that's really, really close. That's called ab initio quantum mechanics, where you can use computers, and we won't get into that right now. We can't solve it completely. Even now, we can't solve it. And that was one reason why Bohr's theory just kind of crashed and burned past hydrogen, because it was basically a many body problem at that point. But Bohr has some other issues here. Okay? One of the issues that Bohr has, basically, it's a conservation of angular momentum thing. I'm not going to present the proof to you because you don't want to see it and I don't want to show it to you, but without all the math, basically it comes down to this. An accelerated charged particle radiates energy. Okay? Take that as an axiom, for this. Okay? Well, is my electron being accelerated? Well, acceleration is what? A change in velocity, or the first derivative of velocity if you happen to be in calculus. So I've got an electron and it's whirling around my little proton, like so. Is my electron being accelerated? Well, yes. Okay, it might be going the same speed. If I change speed, then I am accelerating. Okay, either accelerating or decelerating. Mathematically, if you slow down, you're accelerating because you're changing your speed. But velocity is two things. It's not only your speed, it's also your direction. So I can be going 60 miles per hour east, and all of a sudden turning my car 60 miles per hour north. Don't do that. That's probably dangerous. But you're accelerating. Your speed didn't change, but your direction changed. Okay? Well, this electron is whirling around this proton like here. It's kind of like a tennis ball on a string, and I'm whirling around my head. What keeps the ball whirling around? Well, the pull on the string, right? What if my string breaks? Does the ball continue in a circular orbit around my head? Well, no, it flies off in a direction here tangent to the circle. Okay, that's inertia. All right, well, what keeps this electron whirling around the proton? Well, the fact that opposite charges attract here. Okay, this electron wants to go this way. The proton wants to pull it in like that. So it's a compromise. What happens is the electron kind of goes this way. Do you see that the electron is constantly trying to fly off in a tangent to the circle, and it's constantly being pulled in by the proton, and so it's constantly changing direction. And if it's constantly changing direction, the path it takes is this circular path. All right, well, that's acceleration because I'm changing direction. That's a charged particle. What do we know? We know that an accelerated charged particle radiates energy. Okay? So, if here's my little electron and it's changing direction, so therefore it's being accelerated, I know it's going to radiate energy. If it radiates energy, it has less energy than it had before, conservation of energy. So where am I going to find it? Well, I'm going to find it closer to the nucleus. Well, if it's constantly radiating energy, that means it's going to be constantly closer to the nucleus. So what should the path of the electron take? Well, what it should take is this. It'll go this way. It'll get closer and closer and closer. And it will take kind of a spiral, kind of a death spiral path until it collapses into the proton and has no more energy. Well, I know the charge here. I know the charge here. I can actually calculate, just using plain old 1700 Newtonian physics, exactly how long that ought to take. Right? And that is less than 1 times 10 to the negative 8th of a second. So we know that atoms can't look like what Bohr postulated. Why? Well, if they did, number one, you shouldn't see a discrete spectrum. You shouldn't see certain wavelengths of light being given off. What you should see is this just big, giant flood of photons coming off of all sorts of wavelengths, because that electron is just getting closer and closer and closer, just emitting photons off as it goes. So what would the universe look like? Well, it'd be a very bright place. You just see this bright flash of white light, as the electrons are falling into the nucleus. And that should happen in 1 times 10 to the negative 8th of a second. We know that doesn't happen. Why? Well, because you're still here. You're made of atoms. If all the atoms in your body collapsed in 1 times 10 to the negative 8th of a second, you wouldn't be here to see it. The entire universe would essentially be one big giant flash, and then it would be over. We know that's not true. we know that atoms are a lot more stable than 1 times 10 to the 8th of a second. They hang around. So there's problems with Bohr's theory in that it only works for hydrogen. And not only that, I can use plain old 1700 Newtonian physics to prove to you that an atom can't look that way. But at least we're making progress. So what do we do now? Well, that's what we're going to talk about in the next video. We're going to talk about something called the quantum mechanical model. Okay, so you can impress your friends and tell everyone you're studying quantum mechanics, because that's where we're headed. A lot of serious math in this one, but we're not going to do it. I'm going to try to take all the math out I can in this. But yeah, you can really get in some differential equations on this stuff if you want to really hit it full speed. But that's where we're going to go from there. We'll talk about the quantum mechanical model. So hey, we're up to 1900. So I guess only another century to go here, right? All right, so we'll talk about that next time. I'll try to explain it as simply as I can, and then we'll get to electronic structure, which is really where we're trying to hit. So we'll see you in the next video. Bye.